Good afternoon, everyone. My name is Wang Xiaochen. Today, I would like to present our work on LLMDYara, LLMs-driven automated YARA rules generation with explainable features and DNAHash. First, please allow me to introduce our team. We are from Alibaba Cloud, one of the most leading cloud service providers globally. This work involves 4 researchers. First, my co-speaker, Liu Yiping, who will later present the second part of this work. In addition to her, we have 2 other contributors, Wang Xiaoman and Cheng Cong, who could not be with us today. They are both excellent security engineers, and all of us currently work on malware analysis at Alibaba Cloud Security. When it comes to the malware analysis, in recent years, the number and the diversity of malware have been growing rapidly. It's more difficult for security analysts to rely on traditional manual methods for rule-based detection. As a result, automated rule generation methods have been proposed. Most existing automated rule generation methods focus on YARA rules, which are the most common static detector tools. Their approach uses machine learning or deep learning to extract static features. For example, YARA focuses on string-based features, while the AutoYARA handles byte sequences well. However, this still faces challenges in rule quality, false positive rates, and the interpretability of features. To address these issues, we propose our solution, LLMDYara. In summary, we face the same following challenges. First, how to reduce the false positive and improve raw quality. Second, how to make selected features more interpretable. For example, we hope the selected features have meaningful semantics and related to the sensitive behaviors. Finally, large models show strong performance across domains. However, how to unlock their prediction for automated rule generation is a still major challenge. So in light of this challenge, we will introduce our solution, LLMDYara method. First, we broke down the task into 4 parts: feature extraction, feature filter, feature decision by large model, and rule generation. Specifically, this is the framework of LLMDYara. As shown in the picture, feature extraction models extract 3 types of features: string, function, and field DNAHash features. Then the next filter model uses a pre-collected benign simple database to filter string and DNAHash features and identify third-party or sensitive codes to filter function features. In the feature decision model, a large model is used to select string features, identify function behavior, and extract opcode sequences. Finally, the last model generation rules is based on the evaluation results and the feature distribution. Now, I will present each model by addressing the problem and the corresponding solution. First is the feature extracting model. String features are commonly used in the YARA rules. So, how to define and extract high-quality strings? We first define 17 IOC-related string patterns and extract these features, and it is based on our expert knowledge. And we then collect all strings with a minimum length of 6 characters. To improve the meaningless strings, an NLP model is designed to identify natural language strings. Overall, the string features in LLMDYara are classed into two types. The first is IOC-related strings, and the next is natural language strings. So besides the string features, what other features can be extracted? The first idea to come up was extract function features. Since large models are better suited for analyzing decompiler code, but the generation rules are based on the assembly code, so it's important to connect them. Therefore, during feature extraction, we include address offsets and the line number information with the extracted decompiler code. During the third model, the large model will output the line numbers and the size of the selected sequences by using the offset information. A mapping to the corresponding assembly code can be established. A more detailed explanation of this process will follow in the third model. Notably, if the function decompiler failed, we just directly extract the assembly code. Additionally, a function call graph is extracted partly to provide the large model with the connection information, and the other is to assist in generating rules. More details will be also given in the rule generation part. However, in the presence of challenges such as self-modeling code, string and function features are not usable. So what alternative features can be used while controlling false positives? To address this issue, we introduce a new feature called the field DNAHash feature. The feature calculates hash values for different parts of the binary field based on its structure, resulting in a set of field DNAHash features. So the feature extraction model provides an initial set of features. To make the large model work first, LLMDYara addresses a feature filtering step as the second part. For string features, we observe that there are many entries in the natural language string. To improve more information for rule generation, we filter deeply these strings into more specific subtypes, such as sensitive APIs, format strings, and so on. In addition, we maintain a benign simple report at the several million scale. By building a feature database from these benign simples, we filter out string features that frequently match them. However, that is one point to note. A single feature matching to benign teams is not a concern, because many such features may together form a good rule to detecting malware. For function features, the question is, how do we decide which functions are more valuable? However, define what makes a function valuable or sensitive is not an easy task. After all, if we have already the valuable function features, we just generate the detection rules. So we filter the function features from positive and negative aspects, and the resulting functions are called suspicious sensitive functions. First, we aim to filter out library functions. On the one hand, we can directly use the capabilities of the disassembler, such as some APIs of IDE. On the other hand, we design a function signature algorithm called Finger, and build a third-party function signature database. So we use this signature-based approach to filter out the library functions. In addition, we aim to directly identify some suspicious sensitive functions. First, we start from the main function and extract the sub-functions it calls. Second, we use the open source static rule metric tool called kappa and apply its rules to mark partitionally sensitive functions. Third, we design a function importance evaluation algorithm to select functions that call more strings or are called more frequently. By comparing signature-based filtering and the collection of suspicious functions, we complete a filtering of function features. After feature filtering, we expect the large model to provide decision-making information for row generation. For strings, we ask the large model to select the top key useful features for row generation. However, our tests show the large model are not good at such specific tasks, so how to fine-tune the large model? First, we can construct a database using YARA rules accumulated over the past years and select many strings from the benign samples. During fine-tuning, we first use SFT method to help the model understand the task and follow the designed output format. We then apply the GRPO method to adjust the model. Finally, we resolve two issues: unexpected features and invalid output format. Next, my co-speaker Liu Yiping will present the left part.
Thank you, guys. Function features are important for creating explainable rules with low false positives. So what types of functions and which opcode sequence within them can be used as function features in YARA rules? Our rule generation framework works at the malware family level. So like YARA-gem and AutoYARA, which looks for common streams or shared binary bytes, we first cluster the functions across family samples with the SSDIP hash of function content. Then we pick the cluster centers as representative functions and feed them into the LLM for analyze. We break down LLM analyze task into 3 steps. First, analyze the given pseudocode and the context information. Second, based on the analyze, label the function and explain the reason. And third, select the code segments from the function that are suitable for generating YARA rules. In the prompt of text part, we provide a series of labels and explanations for common malicious behaviors. If the model believes a function matches one of these behaviors, it should give the representative label. Besides the pseudocode, we also give the function context information, such as kappa labels of its sub-functions and the global variables it refers to help analyze the function. For the model output, it should include the function label and the explanation and the line numbers and lengths of the code segment suitable for a part of YARA rules. And the left button is an example from a backdoor malware family. This function performs an child decryption operation. This model suggests line 19 to 25 is suitable for opcode feature. This family was covered by our human experts' handwritten rule before, and they used the assembly instruction at line 20 in the same function as one of the key features. which is also included in the LLM suggestions. And after getting the model's suggested line numbers, we first map these pseudo lines back to the corresponding assembly code. These assembly instructions may not be continuous. We then convert the opcode sequence into YARA signature, applying wildcards to displacement and removing stack balancing instructions at the end or the beginning of the functions. And here is an example from pseudocode to YARA signatures. Through our experiments, we found that Queen 3 32B model performs very well in identifying function behavior and assigning correct labels based on pseudocode and the context information. However, if there are strict requirements on model response speed or the cost, we suggest use Queen 3 as a teacher model to generate high-quality training data for fine-tuning smaller models. The label information comes from two sources, the dynamic behavior sandbox and the kappa static analysis. These sandbox provide ground truth behavior labels for each training sample. And we can use Queen 3 model to label the functions in our training set. If the model's label is in the list of behavior detected by the sandbox, we will keep the function and the corresponding label. In this way, we can build a data set of real function pseudocode with accurate labels, ready for training smaller models. After the feature extraction, filtering, and selection stages, we will get high-quality features for each sample in a malware family. For opcode and string features, we use a two-dimension clustering method based on both files and features to find frequent patterns within the family. And for DNAHash feature, we apply a hierarchic clustering, setting the maximum number of different hash segments between files to identify shared hash segments across files. Once the clustering is complete for all three feature types, we will combine the results with rule scoring mechanisms designed for each feature type and generate the YARA rules. If situations where there are strict requirements on rule count and file size, for example, in our business situations, rules need to be updated and deployed frequently. There is a rule compression part, including two steps, subset compression and the intersection rule merging. This helps combine similar frequent patterns and reduce the total number of rules. Here below are two examples from the final YARA rules generated by our system. And this one is in the bottom is the native version, and the other includes the DNAHash module. The experiment part. In the experiment, we compare our rule generation method with two open source tools, YARA and AutoYARA. The comparison includes the detection rate and false positive rate on our collected set of 2.3 million benign samples. To ensure a fair comparison, we remove the feature filtering step in LLMDYara in all experiments. This avoids any advantage from using a large set of clean files during training, which the other tools don't have access to. In experiment first, we use a public malware dataset collected from 3 open sources after 2025. For each family, we randomly picked 1/3 of the samples and up to the maximum of 1,000 as the training set, and used the rest as a test set. Here we show the detection performance of 3 tools on the top of 60 families by sample count for both training and test sets. The heat map below shows detailed detection results on the top 30 families. As you can see, LLMDYara performs better than the other 2 tools in both the training and test sets. And on the left is a bar chart, shows the average detection rate across all families. YARA-GN refers to YARA-GEM's simple rule mode, which allows to generate simple rules for files included in super rules. While this mode achieves a high detection rate, it also produces significantly more false positives compared to the other tools. We separately evaluate LLMDYara's native YARA rules mode and the versions enhanced with DNAHash. The results shows that DNAHash can help improve the detection rates. But even when using only the native YARA rules without DNAHash, LLMDYara still performs better than YARA-GEN and AutoYARA. Here, we test the rules generated by the 3 tools against our collected benign sample dataset to measure the false positives. As shown in terms of both the numbers of false positive samples per family and the total number of false positive samples, LLMDYara performs significantly better than the other 2 tools. And these results shows that using interpretable function-level features can help reduce false alarms, making the generated rules more precise and reliable. And here is a detailed example of a rule generated by the 3 tools for one family among the top 30 recent active malwares. In this family, the common string across samples are system API names. These strings are filtered out by YARA-GEM's built-in string whitelist. So YARA-GEM has to rely on the rare and special strings that appear only in a few samples. This results in a low coverage for this family. Although LLMDYara's rules also use these API streams, it includes the child decryption function as a key feature. This allows the rules to achieve a 100% detection without any false positives in the benign sample dataset. AutoYARA also performs well on this family. However, LLMDYara's interpretable rules reveals that the malware family may have behaviors such as self-decryption, process injection, and modify files or registries, information that goes beyond detection. This makes our rules not only effective for detection, but also useful for explaining alarms in real-world situations. We noticed that AutoYARA's paper provide the dataset used in their experiments, so we also run the same comparison on AutoYARA's public dataset, and the results show that on this dataset as well, LLMDYara performs better than the other 2 tools in both detection rate and false positive rates, further confirming the effectiveness and the robustness of our approach. And here is the false positive results on the benign dataset. And we leave our email here for these who are not on site or for any follow-up questions. And we got